Hello everyone. In our second video on computer vision based control of robotic manipulators, we are going to talk about how to design the control law to move the end effector to the position and the orientation that we want so it can basically perform its job. Let's say if it's a pick and place or handling some objects and so on, the best way it can. In the previous video, we learned that the approach we are going to take is called image-based visual servoing. So we are not going to reconstruct the 3D environments or 3D model of the object to be handled. We're just going to work with the 2D images, and we try to create basically what we call a position error. We're going to see that in details in this video. We're going to basically connect the camera to the end effector frame. It might not be exactly at the end effector frame. It might have some fixed orientation and displacement, but again, it is attached to the end effector, so we call it a camera in hand. We'll learn also about the pinhole model and the perspective projection of the camera and the image formation. We'll learn about feature points. We'll learn about finding the orientation of an object, the centroid, the command region props, and so on. So we'll learn a bunch of these details in the previous video. And now the question is, well, how would you design a control law here? Okay, so let's talk about that. The first thing we need to learn here is called the interaction matrix. What is that? So let's say the location of a specific feature point in the image, in the current image that the camera attached to the end effector can see, we show it with S of t. S is U and V, and remember U and V were the horizontal and what? Vertical position of any point. So if we put those in a vector and call it S, right, image coordinate, basically that's what it is, image coordinate, right? If I call it with S, the question is, what is S dot? S dot is what we call image velocity or image feature velocity. The unit for this S dot is millimeter per second, right? Because remember, S is U and V. U and V, they had units of length. So the unit for S is unit of length, let's say millimeters, right? So if I have unit of millimeters for this, then the unit of S dot is going to be millimeter per second. There is a term in computer vision and image processing. It is called optical flow, which is very closely related to this S dot. Optical flow is similar to that. It's the motion of the pixels, it's the motion of the points, feature points, in an image, but the unit of that, instead of being millimeter per second, it is pixels per frame, really. So you clearly can see these two are related, because remember that each millimeter in your image plane corresponds to so many pixels. The relation is created by those two parameters, if you remember, Sx and Sy, correct? So if I basically divide U and V by Sx and Sy, now I get them to be what? Pixels per second. And if I want to go from seconds to frame, I need to multiply by frame rate. So if I divide my S dot by X and Y, let's say I do dot division by Sx and Sy, so the U dot by Sx and the V dot by Sy, right? This is pixel-wise division. The unit of this guy is now, as I told you, is millimeters or pixels, I'm sorry, per second. But I want pixels per frame, so all I need is now to multiply this by frames, seconds per frame, or divide it basically by frames per second. So if I divide this whole thing by the frames per second, Now the unit of all of this is going to be what? Pixels per frame, which is a very important thing in computer vision called optical flow. So you see this S dot is very similar to that. It's just a couple of division by constant numbers. They are proportional to each other. The bigger the S dot, the bigger the optical flow. And it shows really how much each pixel, each feature has moved from one frame to another, from one picture to another per second or so on. And again, all you need to do is to go to the computer vision toolbox, go to the examples, and one of the topics of it is called motion estimation, right? Which if you go down, you should be able to see it's called tracking and motion estimation. And here is where the topic of optical flow can come in, as well as tracking specific feature points. Okay, so these are specific feature points that are being tracked, not really the calculation of optical flow, because what optical flow is not just specific points in the image that the optical flow calculates, it's their motions, it's all of the pixels. So optical flow is like a vector field. It is a vector field with two components, and those two components are the horizontal and vertical velocities or displacements of the pixels per frame. Okay, and so although here you see that topic, but it's not exactly that, right? All you need is to go back here and look into the optical flow, which should be, let's say here, motion estimation, and you have the optical flow, and this one will create for you, as I said, a vector field. It shows how much each pixel by how much of intensity and in which direction it has moved from one image to the next. Here is also another example of that, right? So you see the cars running on the highway, and you have a fixed camera taking their images and calculates their motions in these images. And then using that, it can detect which parts of this image are moving, which parts of it are constant background. So it can detect moving objects in the stream from a camera, which parts are moving, which we call foreground, which parts are stationary, we call background. This is, for example, not only with these images, you can calculate, if you know the distance from your camera to the cars, you can detect the speed, the actual speed of these cars, right? Their speed in the world coordinate, as well as which parts are moving, which parts are not. So this is another way to detect motion. It's called motion detection. Not only we have all sorts of motion detectors that are based on basically capacitors or magnet stuff, you also have camera stuff that can detect moving objects versus constant background. If you want, you can even look at this demo here that reads that video and then show you basically the optical flow. So I recommend, if you have interest, go and look into the topic of optical flow, which is very closely, as you see, related to this image feature velocity S dot. Now, how is this S dot related to the robot motion? Well, in our case, the camera is attached to the end effector. So whatever the end effector velocity is, V's and omegas, it could be very similar, the same as what? The camera velocities, right? Because if they are rigidly attached to each other, whatever linear velocity or especially angular velocity that the end effector frame has, it's going to be the same angular velocity that what? The camera frame does, and the same for linear velocity because they are rigidly attached. So here we show the camera velocities, right? The camera velocities V and omega, we show it with xi. Again, this xi is very closely related to the xi of the end effector. They could be identical if and only if the camera frame and the end effector frame are identical, which barely happens in real life, that your end effector and your camera frame are identical. Their origins are the same, their orientations are the same. We learned that that cannot really happen. Why? Because the end effector typically has a tool attached to it, like a gripper or something, and the camera cannot be at the center of the gripper, right? You remember that? We talked about it. So when this gripper is going to come and grab something, if you remember, your camera is going to be attached to it, but not exactly at the center of the gripper. As you can see here, it is going to be on the side of it. So they are attached, but they are not identical, right? So the xi of the end effector and the xi of the camera frame are not exactly the same. They are closely related. How are they related? Let me talk about that first, and then we come back and talk about this S dot term again. So if the two frames are not identical, then we can relate them to each other here. So let's say that my camera frame and the end effector frame C and E are related by a homogeneous transformation. Given by a rotation matrix, they are not exactly the same, and an origin difference, D of C with respect to E. Okay, so these two are constant because they are rigidly attached. These rotation matrix and that displacement vector are constant, right? Now, the xi that I just told you, the xi of the camera, is this guy. Xi of the camera with respect to its own frame. The xi of the end effector, which we show it with xi of E in E, is related to the velocities of the camera. The end effector velocities are related to camera velocities, but using what? Using a 6x6 transformation matrix. Remember, xi is 6x1. It's a twist. Xi is a twist. So this xi of C in C is 6x1. Xi of E in E is a 6x1. How do I relate these two together? Of course, using a 6x6 matrix. What is this 6x6 matrix? And it's a block matrix, so it has 4 elements. Each one is 3x3. And what are these? On the 2 diagonals that I have, it's the same rotation matrix, R of C with respect to E. In the bottom off diagonal location, you have 0, 3x3. And in this other off diagonal element, 1 and 2, you have what? You have skew symmetric matrix of this vector D multiplied by the rotation matrix. Okay, so if you use this transformation 6x6 multiplied by xi of the velocities of the camera, you get the velocities of the end effector. And this is the velocities of the end effector written with respect to its own frame. What we really need is xi of the end effector in base, in frame 0. This is what we have calculated in what? In differential forward kinematics. This xi is the one that we talked about in differential forward kinematics, end effector in base. How do I take it from this EE into E0? Again, all you need is another 6x6 transformation matrix. And this one is a diagonal block matrix. On the off diagonals, we have 3x3 zero matrices, and on the diagonals, we have the rotation of end effector in base, which comes from forward kinematics, right? So remember, at the end of the day, you need to control your robots. When you control your robots, the control of the robot that we had in all of our previous lectures is this guy. It was based on this. Velocities of the end effector in base. It was all based on that. What we are going to work right now is this one. The camera velocities in its own frame. So before I can really move my robot, I need to go from here to here and from here to here. Once I know this, then I can command my robot to do whatever it has to do. But the control law that I'm going to design is here. The robot motion or the robot commands are going to be based on this. So whatever I do in the control law, I need to do two 6x6 transformation matrices to relate it to the robot motion. Then I can command my robot to move. So please keep that important thing in mind, because most of the time this D is not a 0, 0, 0, and this rotation is not an identity matrix. These are non-zero yet constant numbers. Okay, so that is a very important topic that we have to discuss ahead of time. Good. Going back, the question was this: what is this S dot? If this S dot is the image velocity, right, image feature velocity, and xi here is this xi is xi cc, is v and omega the camera velocities, can I relate S dot to xi? And the answer is yes, I can. How? The relation between S dot and xi happens through a 2x6 matrix, which we call interaction matrix. Remember, S has 2 components, so S dot has 2 components, xi has 6 components, so L has to be a 2x6 matrix, which we call L matrix, L of S and Q. It's not even a constant matrix, it's a variable matrix. The entries in that do change with time. So how do we relate them? Here, consider that P equal XYZ transpose is the projection on the camera plane of the fixed point P0 in the word frame. Going back to the picture we had, we are talking about this point, this P, right? This P that you can see here is what? Is the projection of fixed point P0 in the word frame, right? First of all, that point is a fixed point, okay? And remember from this bottle example that we had in the previous video, let's say it's this point here. The bottle is fixed, it came fixed on the conveyor and it is stationary now. That's point P0. First thing I need to do is I need to take this fixed point P0, for which I know the coordinate of it in the word frame. I need to project it into the same point, but now in the what? In the camera frame. And all I need to do is a rotation matrix, right? I need to do a rotation matrix, which is basically, if I want to go with that, then this is equal to whatever I had in the word frame. I need a rotation matrix R of W with respect to C, and I also need to add what? D, correct? And this D is going to be D of W with respect to C. Okay, and these are those extrinsic camera parameters that I mentioned in the previous video. So if I can find the coordinates of a real world point, a stationary real world point in the camera frame, and I call this point what? X, Y, and Z, as you can see here, right? What else? That's the first thing we need, P. The other thing is the angular velocity and the linear velocity of origin of the camera frame with respect to the word frame. I show them with O dot. So O here, O dot means O dot of camera in the word frame. If I show the speed of the center of the camera frame in the word frame by what? Vx, Vy, and Vz. And omega to be what? The angular velocity of the camera frame in the word frame, showing it with omega x, omega y, omega z. Then from kinematics, we can write that what? PO dot is equal to P dot plus omega cross P plus O dot. What is this? Let me show you that one as well. So here I have a word frame, right? Let's say X of word, Y of world, Z of world. I have a fixed point P0 in this word frame. On the other hand, I have the camera frame, right? So here, this is my camera. And this camera has its own set of axes. It has its own origin and everything. So here I have point O, which is this point. That's the origin of the camera frame. Let's see if my, yes, that's O. So I can write this vector P0 as what? As vector O, which goes from origin of the word frame to the origin of the camera frame, this vector O, plus vector P, which is this vector. Remember, P was the point in the camera frame. So I can say this vector P0 is equal to vector O plus this vector P, right? So let's write it down here. So P0 is equal to P plus O, or O plus P, let's say. Now, if I take time derivative from both sides of this, what's going to happen? P0 is a fixed world coordinate point, so time derivative of that is 0. That point is stationary, does not move. By the way, this time derivative that I'm taking is with respect to the world coordinates. Good? What's the derivative of vector O? O belongs to the centroid, the center of the camera frame. It's a single point, so O is going to be O dot, of course, which here we showed with Vx, Vy, and Vz. What about P? How does P change with respect to time? Well, P, remember, it has components x, y, and z. And these magnitudes of x, y, and z can change. Why? Because this P is with respect to the camera frame. It is measured from the camera. And when the camera moves, because point O moves, or it does what? It does rotate, then the magnitude of x, y, and z can change, right? So P can change with respect to time either because the magnitude of component x, y, and z are changing, or the other reason is no, the magnitude of them is not changing. The distance of point P0 to the base of the camera is fixed, but the camera is showing what? Rotation. And that rotation also causes the x, y, and z to have time derivatives, and that is going to be omega cross P. If P has a constant magnitude, because the camera origin does not move, point P0 does not move, the rotation of the camera causes this extra term. And this is what you learn, hopefully, in dynamics, right? The velocity of a point in terms of what? Frame A or a frame B, where frame B has a rotation and a translation with respect to frame A. So hopefully you have seen this guy. Again, in this case, P0 does not have time derivative because we consider P0 to be a stationary point. The only thing that does change and does move and rotate is the camera. So if that's the case, this is what you see here. And if from here I calculate P dot, which has x dot, y dot, z dot in it, based on the two other terms, it's going to be negative omega cross P and negative O dot. O dot is clear, Vx, Vy, Vz. P itself is xyz, omega is omega x, omega y, omega z. If we carry out this and simplify the result, this is going to be the result. This is the time derivatives of xyz based on the xyz themselves, and vx, vy, vz, and omega x, omega y, omega z. So far good? Now, what is S dot here? S dot is U dot and V dot, because S itself is U and V. So S dot is going to be what? U dot and V dot. Now, what is U? We had U in the beginning, in the previous video. U was what? Lambda x over z, and v is what? Lambda y over z. So can I take time derivative of these? Of course I can. What is time derivative of u? U dot is going to be, lambda is constant, so now you have a ratio. And derivative of a ratio, you know, it's derivative of numerator times denominator minus derivative of denominator times numerator divided by denominator squared. And similarly, you can do a similar thing for v and get v dot to be lambda, and then it's going to be y dot z minus z dot y divided by z squared. Right? So these are the derivatives of u and v, or the s dot components. But now, can I replace the dot terms, x dot, z dot, and y dot, z dot, can I replace them from this new set of equations that I found, these guys? If I can, if I combine equation 2 and 1, then these are the resulting equation that I will get, u dot and v dot, or the whole vector s dot. The first component of that is like this. The second component is like that. Now, can I write this S dot as what? A matrix L times what? Times xi, where xi is what? Xi is V and omega. So it is like Vx, Vy, Vz, then what? Omega x, omega y, and omega z. Of course I can. All I need is to look at the coefficients of these terms in each one of the u dot and v dot. Look, how many vx do I have here? Negative lambda over z. How many vy do I have? None. Right? How many vz do I have? U over z. How many omega x? None. How many omega y? This much. How many omega z? Some of these two. And that's what exactly, as you can see, if you put it there, this is going to be your first row of this interaction matrix L. And if you go and similarly look at v dot, those will give you the second row in this interaction matrix. So that's how you can establish a linear relation between the camera velocities and the feature point velocities using a matrix we call the interaction matrix L. As you can see, this matrix L is not constant. It is a function of u and v, the image point location, u and v, as well as what? Z, the depth of the point in the camera frame. Lambda is a constant number, it doesn't change, but u, v, and z do change. Okay, so this interaction matrix is not a constant matrix. Okay, by the way, I found a small typo. This component here, this coefficient of omega x is u v over lambda. That was not omega z, that was omega x. So this term here is not 0. This term is u v over lambda, which you can see over here. Okay, so I found the interaction matrix, fine. Before I go over how I use this interaction matrix to establish the robot control, I need to mention a few things about this important matrix. 1, this matrix, as I just told you, is not constant. It does depend on u, v, and z, okay? And one of the important things is z. If I have a feature point in the image plane, for which I know its coordinate is u and v. I found it using a feature feature finding matching algorithm like SURF or SIFT or something I mentioned in the previous video. Then I know it's u and v. So finding u and v is not the hardest thing, right? I have algorithms that can detect points and they can match them. So finding u and v is not hard. The hard thing is z. Z is the piece of information that you lose when you go from 3D world to the 2D image plane. It's the depth. That's what you lose, right? Z is the depth. So since I lose it, calculation of this L matrix is not really practical unless you have a way to estimate this Z, right? And here there are several ways that you can do it. One is you have more than a single camera, so maybe attached to your end effector you have two cameras instead of one, and here you can use stereo vision and you can use triangulation and then estimate the Z of the point. Okay, so one of the methods that you can estimate this Z is stereo vision. Again, it's a topic of its own: stereo vision, disparity map, and depth estimation from stereo vision. That's one way. The other way is to use basically tools that can give you depth or range, right? And that is using range sensors, like a LiDAR, like ultrasonic, or so many other things, especially LiDAR. Or you can use the new kind of cameras we call RGBD camera. They are a regular red, green, blue camera plus depth. Like what? Like the Kinect that you have on your game console, right? Or you see in Turtle robots, Kwanzaa robots, and so on. This is an overlap of red, green, blue, and depth value for each pixel. If you have an RGBD camera, then if you know the location of a pixel, U and V, you can also, in addition to U and V, you can also get what? Z from that RGBD camera. Then calculation of the L matrix is not that hard. But in general, remember that because the Z is there and it's not even in the numerator, it's in the denominator because of perspective projection, calculation of the interaction matrix is not trivial. Okay, you have to have a way to estimate Z or compensate for Z or something like that. Okay, that's one thing you need to know about L. The other thing is this L matrix is 2 by 6. It does not have full rank. The best this guy can have, the maximum rank of matrix L that you can have is 2. What does that mean? It means not every motion that I can have for the camera, Vx, Vy, Vz, omega x, omega y, omega z, not each and every one of these motions is necessarily make that pixel what? Move in the image plane. Okay, because I'm going from a 6 by 1 space to what? A 2 by 1 space. So not every motion in the 6 by 1 space will cause a change in the 2 by 1 space. Remember, the rank of the connecting matrix is 2 at most. So you clearly can see, for example, some of that using the zero numbers. What does the zero mean? It means, hey, regardless of how much I move my camera in the y direction, it is not going to change u dot. The horizontal component of the feature in the image plane is by no means affected by the velocity y component of the camera in the world. On the other hand, the v dot, the vertical velocity component of the feature, is by no means affected by what? By vx. So clearly you see it because of the zeros. Also, if one of these u or v happen to be 0, of course, in an image plane, you never have u or v equal 0. The minimum of them is 1. It's not going to happen that they are equal to 0, right? So it's not really that u over something or v over something or uv over something is going to be 0. No. The same thing for these terms, which are always positive, and lambda is positive. But these two components, vx on v dot, vx on v dot, and vy on u dot, the contribution is always 0, and sometimes a linear combination of several of these, some of that could have a 0 effect on u dot and v dot. Okay, so not however you want to move the camera, it necessarily makes that feature point move in the image plane. Keep that in mind. Good. So fine. These are all important things that we have about the L matrix. One other thing I need to mention before the control law is, what if you have more than one feature point, right? Most of the time you don't have one feature point, you have several feature points, right? Remember the cameraman example that I showed you? If you remember, in the cameraman example, I had what? I had several feature points, and my goal was to track several of this. And if that's the case, then what? For each one of them, I have a similar relation. Oh, sorry, I went to the wrong toolbox. It's supposed to be computer vision, not control. They're very next to each other. Then for each and every one of those points, u and v, I have what? I have u dot, v dot, and I have a specific L matrix. So can I combine these all together in a giant matrix? The answer is yes. How do I do that? You can see here. Let's say I have more than one point. Let's say I have n points, n feature points I'm trying to track, or I want to get them to the position I want. So I showed the coordinate for the first point with u1 and v1, second one u2, v2, all the way to the nth one, which is un and vn. And the depth for each one of these points as z1, z2, all the way to what? Zn. Then, how do I relate s dot, which is what here? This s dot here is like u1 dot, v1 dot, the feature velocities of the first point, u2 dot, v2 dot, all the way to what? To un dot, vn dot. Can I relate that now to xi? Because all of those come from the same xi. Yes. In this case, my xi is still 6 by 1. This guy, instead of being 2 by 1, it is what? It is 2 times n by 1. Right? This s dot is 2n by 1 because I have n points. Each one has 2 entities. So what's the dimension of this relating matrix L? Clearly from here, the dimension of the L has to be what? It has to be 2n by 6. So when multiplied by 6 by 1 gives me 2n by 1. 2n by 6, how can I make it? Well, if you remember, the simple L matrix was what? It was 2 by 6. This is what I had for a regular L matrix for a single point. Now what would you do? This is the L for the first point, if you compare it against the formula. This is L of the first point. Then right below this L of 1, you put what? You put L of 2. Right below that, L of 3, go all the way down to what? L number n. And now what's the dimension of this? Remember, each one of them is 6 by 2, or 2 by 6, I'm sorry, 2 by 6. And you have n of that, you have n row of that. So this guy is going to be multiplied by n. So now this giant L matrix is going to be what? 2n by 6. And that's what you have here, the combined L matrix. Okay, so this is how you combine individual L's for these feature points and combine them all into a giant L matrix. And what's the advantage of this giant L matrix? Well, if I just have 3 points, if I just track 3 points, what's going to happen to L? Guess what? It's going to be 6 by 6. So now my S dot, which is going to be 6 by 1, is going to be this L combined 6 by 6 multiplied by xi 6 by 1. And what's good about this? If I can calculate S dot from my image tracking algorithms, from my computer vision algorithms, so I can get this one calculated, as well as L, I can get also this one from my RGBD cameras. What can I calculate? There we go. I can calculate my xi. My xi is going to be what? It's going to be L inverse times S dot. Or if I have more than 3 points, so this guy, instead of being 6 by 6, it's going to be like 8 by 6, 10 by 6, 20 by 6. Then I have more points than I need to calculate what? The camera motion, xi. Remember, xi is what? The camera motion. So if I have more than 3 points, then what I need to do is to basically, because I have 6 unknowns, but I have a lot more than 6 equations, then I use a least square solution, and instead of finding xi by L inverse times S dot, I use what? I use L pseudo inverse, L plus times S dot, which is the left pseudo inverse is L transpose L inverse times L transpose. Okay, fine. So I calculated my camera motion, or the required camera motion, right? Based on what I want, I calculated my camera motion. What should I do now? Remember, when I know my camera motion, based on what we just discussed, now I can take that camera motion into end effector motion, first described in end effector frame, then described in the base frame. And once I know this, can I now control my robot, control my joints, such that my end effector velocities are like xi? Well, absolutely. How do I do that? Now this is the time to talk about the control law. So let's talk about it. If I calculate my required camera motion, now how do I design my control law? This is what I do. So here I use an error-based approach. I say, let's say the current position of a specific feature point is S, but I wanted it to be at SD, like I wanted it to rotate 30 degrees or whatever, go from one point to another. Remember, we talked about all of this in the previous video. So this is, let's say here, this black is S. I wanted it to go to SD. This is for feature 1. Then I can go to feature point 2 and repeat the same thing and so on and so forth, right? So if I know that, the difference between them, I call it the error in the feature location, E. Good? Now, all I need to do here is a simple proportional control to achieve stability and convergence of error to 0. So what do I do? Here, I design my control law in an inverse manner. How? I first start from a differential equation that I'm sure will give me asymptotic convergence of that error to 0. You know, the solution to E dot equal negative Kp times E is what? E of t equals whatever it was in the beginning times exponential of what? Negative Kp times t. And this function, when t gets bigger and bigger, that function asymptotically will go to 0, correct? So I know if I could achieve some convergence like this, I will move my camera to the position that it should go. And remember, camera is attached to the end effector, so the end effector will go to the position orientation that it should go. Now, how does this will help me come up with the control law? So what is E dot? E, remember, is S minus ST. So E dot is S dot minus ST dot, right? Here, if I assume my ST is what? A constant location. I want it to go to a fixed location. Then this S dot term is 0. So E dot will simply be equal to S dot. And what was S dot? If you remember, S dot, based on the definition that we had, S dot was L times what? S dot was L times xi of the camera. So if I go back here, and for S dot, I replace L times xi, right? That is E dot. And E dot, based on our convergence, should be negative Kp times E. So I will get what? I will get L xi equals negative Kp times E. This is what I end up with. And then what do I need? All I need is to multiply both sides by L inverse, and that will give me this control law. As long as L is 6 by 6, I can use L inverse. If I have more than 3 points where L, remember, is like 8 by 6, 10 by 6, 2n by 6, where n is bigger than 3, then instead of L inverse, I can use what? L pseudo inverse. And this is going to be my what? My rule to what? The amount of camera motion. Okay, so if I follow this control law, where the amount of camera velocities is equal to negative Kp, Kp is a gain that you choose, L inverse or L star, which comes from the location of those feature points, right? Remember, L is a function of S and Z, correct? Just going back, L is a what? L in general is a function of S and Z, and these guys come from your RGBD camera and your feature tracking algorithm. So you can find L. You decide Kp. Error is calculated based on where they are at the moment and where you want them to be. And that forms error. If you choose your camera motion based on this control law, one of these, depending on how many points you are tracking, guess what? You exactly can tell how much you need to move the camera. And remember, once I know, as I just said, xi in C and C, I can first go xi E in E, and then I go xi E in base, or in the world. And guess what? What is this? This is equal to the Jacobian of the robot times Q dot. So now that I know this one, how can I determine my Q dots? All I need is to multiply both sides by what? By Jacobian inverse, if it's, let's say, 6 by 6 degrees of freedom, or if it's less than that, I can use basically transpose, I can use pseudo inverse or anything. And let's say, for example, if this is a 6 by 6, this is a 6 by 1, then the joint velocities that I need is J inverse times xi of the end effector in the world. So if I can move my joints at this amount of velocity, that's all I need to do to achieve the basically convergence of error to 0. Now here, if I apply this same proportional control law, simple law, to this bottle example where I wanted my feature points to rotate like 30 degrees or something like that, right? Remember, I have these 4, let's say, feature points, and the solid points are the current location, the hollows are where I wanted them to go, which is corresponding to some amount of rotation about, let's say, this center point here, right? Then what kind of camera velocity components does it require to achieve such feature velocities in the image plane? Here, if you look, the main problem that exists here are the amount of displacement along x, y, and z, assuming we started from 0. The main problem is x and y are almost at 0, so you don't need much of displacement about x and y, right? Here we assume that it is attached to a 6 degree of freedom robot, but if you look at z, the amount of z displacement, and the unit here is in meters, the amount of z displacement is about -1 meter in maximum condition. So what does it mean? Remember, z is the optical axis of the camera. So if this is the feature point and this is the camera, about the z-axis, which is this axis here, I need to go back for 1 meter from where I am, right? That's -1 means. So the camera has to go back about 1 meter to achieve 0 tracking error. And that backward motion of the camera is the problem we call camera retreat. It's one of the major drawbacks of this control law, that if you just want to do a pure rotation about the fixed point of the feature points that you're tracking, if that's all you need, it's not just gonna need a simple z rotation, as you can see here. It also needs what? It also needs a big z motion as well, or a big vz, or a delta z really in this case. And in the backward direction, for many robots, such huge displacement is not even possible. Plus, the goal might be, at the end of the day, this camera is attached to my end effector, and my end effector is going to go here and grab this object. If I move back, I cannot even grab it. That's one. Two, moving 1 meter back the end effector might not even be possible for the size of workspace of some robots. And the worst part of the problem is, if this rotation that you see here is about like 20-30 degrees, if this guy goes to 180, so each feature point now has to go to what? To the point that is across from it, something like that. If that is the case, guess how much you should go back in the z direction? Infinite, which is now even not theoretically possible. Okay, so this camera retreat is the big problem, one of the big problems that you have with the simple proportional control law. Because, and why is it? Because, as I mentioned here, this control law, what is it that it controls really? It tries to control the error in the image plane, not the trajectory of the camera. All it tries to control is to make S go to ST, or the error in S go to what? To 0. That's all it tries to track. It has no explicit control over what kind of entries in Xi this simple law will end up in. Although the law looks very simple, but it can lead to huge amount of displacements or rotations in the camera to achieve such thing. And in the case of this camera retreat, it could be so big that they are not even physically possible. Plus, you might say, well, if all I want to rotate these feature points, maybe all I really need is to what? If this camera is attached to my end effector, maybe all I need is a rotation about the z-axis. Of course, it's not that simple, because the equations, as you saw, are not that simple and linear, right? The components of L, they are not that simple. So it's not just one of the entities in Xi that you need to change. You need to change several of them at the same time, as you can see, right? You have theta z, you have theta x, you have theta y. All three of them have to change, as well as your z. Your x and y displacements are barely any non-zero number. They're very small. But you need some big z, and you need some big theta x, theta y, and theta z really, or omega x, omega y, omega z. So, but you don't have any control over how big you expect your camera to rotate. So that's where the more sophisticated algorithm for vision control come in, and those methods are called partition approach. What is that? In one of the partitions approach proposed by Cork and Hutchinson, they say, well, let's separate the motions along or about the z-axis separate from x and y-axis. They say, well, remember my camera has 6 degrees of freedom. Vx, Vy, Vz, omega x, omega y, and omega z. And they say, well, this Vz motion, this one, the camera gets closer to the object or further away. And the spin about this z-axis, we are going to control these separately from what? From omega x, omega y, Vx, and Vy. So that's why partitioning means instead of controlling all 6 degrees of freedom together using a simple control law, which we just saw, the proportional control law, let's control these 6 degrees of freedom using 2 separate control laws, or 3 in this case, control laws. I calculate how much I should move about z in one control law. I calculate how much I should rotate about z-axis in a separate control law. And the rest of them, I follow this proportional control rule that you just saw, this one. Okay, I still use this one. Okay, how? They say, well, let's say here I have a few feature points that I'm trying to track and move them to the desired point. Let's say I have 4 feature points, for example. How do I control my Vz? How do I control my what? My omega z. Pay attention, this is your image plane, so your z-axis here is perpendicular to this plane. So your z-axis, your z, is perpendicular to this axis either out of the board or what? In the board. Okay, your z is perpendicular to this image plane. Good. How do you control V and omega? They say for omega, we do it very simple. We calculate how much each one of these lines have to rotate. Like this case here, right? What I do, I connect each feature point to the next feature point. So I connect feature point I to feature point J, and that gives me a line. Now, if my goal is what? To move point 3, let's say, to this point, so this is new point 3, and point 2 to maybe this point, this is new point 2, this is new line 2, 3, that is old line 2, 3. The angle between these two is gonna be the rotation angle that I need to what? To rotate the line between point 2 and point 3. And that is this entity here inside the parentheses. The current angle that the line has, theta ij, minus the desired angle that it wants to have, theta star. And if that's the case, then what is our reference for measuring the angles? It could be, let's say, the u-axis. So I can measure the angle of both of these lines with respect to the u-axis. So this angle here is theta ij. The desired angle for it is going to be theta ij star, or desired. Instead of desired, you might say star. That's the same thing. Here, star means desired. I subtract these two. That tells me how much this line ought to rotate. And then what? And then I multiply it by a gain and then pass it as to the amount of rotation about the optical axis. Okay? Now you might say, well, which one of these lines would you use? Do you use line that connects feature 2 to 3, feature 1 to 4, or so on? Well, if we consider the object's rigid and camera and everything, which it is, these are all following the same rigid transformation. So if for one of these lines, this entity is, let's say, pi over 6 or 30 degrees, if I do it for the other line, that should be the same thing. Okay? So it does not really matter which one of these lines I use to calculate this error and multiply it by a gain to get omega z, because omega z here, the command is just a scalar command. It's just this should be a single number 1 by 1. This omega kz or k omega z is a 1 by 1. Omega z command is 1 by 1. So really I should use only one of the lines here. Which one? Again, it does not really matter. One thing you might be able to do to make the algorithm robust is to use the average here. So to use basically summation over I and j, right? Correct? And divided by the total number of lines. So use the average rotation that you get from all the lines and use that one to control omega z. So now the rotation about z-axis is proportional to the rotation angle from all of those lines multiplied by a gain. What about v? What's the effect of v? When you make the camera closer to the object or further away, you clearly know the first immediate aftermath of that z displacement is the size, right? If you get close to the object, it might look like this. If you get further away, it might look like this. So the change in the size or the area of a polygon formed by these feature points is the first indication that you are moving about along the z-axis, getting close or further away. So that's exactly how this method talks and say, well, if sigma is the area, if sigma is what? The area or the square root of area of a polygon formed by at least 3 feature points, and sigma star is the desired value for such entity, then the difference between these two multiplied by another gain kvz is how much you need to move about the z-axis or along the z-axis. So first of all, you see it talks about the polygon, not a circle. Why? Because here you have a bunch of feature points that you are trying to track. So let's say this is feature point 1, 2, 3, and 4. So you connect them together, let's say in order, and you get this polygon. Now, if you move your camera a little bit away from the object, then let's say this is what you will get. So the square root of area of this new polygon, you call it sigma star. The square root of the original one, you call it sigma. The difference between these two multiplied by a gain is the amount of vz's, the amount of displacement about the z-axis. And that makes you to get to an appropriate size that you want. So basically you are saying, hey, when the size of the polygon formed by these feature points is equal to this much, it means I am at the right distance, optical distance, z distance from the object. And when the rotation comes to this theta star, then I'm at the right orientation about the z-axis. Okay, so I have controlled my omega z and vz using these two simple rules. And the good thing is when you do so, then your VZ will never go to what? Will never go to huge numbers or infinity, as I mentioned. So it can easily handle what? The camera retreat problem. Now, the only thing that might be a little bit a place of question for you is, why did I use square root? Well, that's because of the units. That's all because of the units. If A is the area, then it has unit of length squared. While sigma is related to V, and V has the unit of length divided by second. So in V, since it has unit of length, the right-hand side cannot have unit of length squared. That's why you take a square root. So this sigma has unit of length, and then this gain has unit of 1 over second. So to make the units on both sides to be equal to each other, that's why you take the square root of sigma. Okay, so that's important. And clearly here you see theta has unit of radians, omega has unit of radians over second, and again this gain k omega z has unit of what? 1 over second. Okay, so you clearly see that in terms of equality of units, everything does make sense. Good, so we have Vz and omega z now under control. Now for the rest of it, which is Vx, Vy, omega z, and omega x and omega y, which we can put them all in a new notation and call it xi xy. And xi z here means omega z and Vz, the parts that I separately controlled. So now this relation that I had, S was equal to L dot equal L xi. Now I break it down into what? S dot equal L xy xi xy plus L z what? Xi z. You see, I'm partitioning the relation into two separate parts. This one I separately control. This one I control the exact same way that I did before. So remember how I controlled the xi, right? If you remember, the formula that I had for xi was what? It was negative kp L pseudo inverse times error. So I used the exact same thing this time for the rest of the degrees of freedom. Look, I used the very same formula, but with some difference. What is the difference here? The difference is I first subtract the degrees of freedom that I controlled separately, which is xi z times Lz. First, I separate it from S dot, because S dot now is sum of these two. So if I want to only control this part, first I take this to the other side and say what? Now Lxy xi xy is equal to S dot minus Lz xi z. I first subtract the part that I have already controlled, and then now my goal is to find this one. How do I find it? All I need is to multiply both sides of this relation by pseudo inverse of Lx y, and that's exactly what you can see here. And that gives me the amount of camera velocity for Vx, Vy, omega x, and omega y. So by combining this rule, these two rules, and this one, I can individually control omega z, vz separate from the rest of the omegas and v's. And now if I do the same experiment I did, and this time to make it worst case scenario, I make the rotation 180 degrees. Remember, if I didn't do the partition approach and I wanted to rotate 180 degrees, what's going to happen? I have to move about the z-axis for an infinite amount of displacement, right? I had the big camera retreat problem. So now if I use the approach by Cork and Hutchinson and do the same thing, this time, as you can see, I'm clearly rotating each feature point by 180 degrees about this point. And if you look here, look at your z. Your z is actually almost what? 0, and your y and x are almost 0. Look at the scale of this number. So I do not really need to move any of my x, y, and z significantly. All I need is to rotate a little bit, right? It's mostly omega z, and that comes from these plots here. This is your theta, this is your sigma, right? My theta started from this value, and you see as I'm rotating more and more about the z-axis, the amount of rotation that I need ultimately goes to 0 because my theta has converged to theta star. And if you look here, my sigma variation is very small because I really do not need to move in the z direction. So my v of z is almost what? 0. So the size of the polygon is not going to change. So the variation in it are going to be very small. And these are the errors that I want. If you look at the error terms, they go all to what? To 0. So I can get asymptotic convergence of error to 0, even for the hardest scenario of rotating 180 degrees. No camera retreat is needed, and the partition approach could handle the difficult experiment very, very appropriately. This is one of the partition approach in image-based visual servoing. It's not the only one, but this is one of the ones that is very easy to understand and to apply. So this field of vision-based or position-based visual servoing, this is a big field. You can have a full course on this topic, and the books by Cork, this professor here, are typically one of the best textbooks when it comes to computer vision in robotics. Okay, so if you want to learn about computer vision in robotics, I encourage you to look at the textbook written by Cork on computer vision in robotics, and you'll learn a lot more about this important topic. I'll try to cover a lot more of that in my future videos, but hopefully this video and the previous one gave you a basic understanding of this topic. Thank you so much. We'll see you in my next lecture.